Hello everyone, welcome back. Today we'll learn how to solve related rate problems. So our goal is then to understand the procedure, we'll see how to solve these, then also to actually do practice with actually solving some and see how this procedure works. So first, explain what a related rate problem is and then kind of this procedure how to do that. So related rate problems, you have these kind of problems, your variables, which are also often your unknowns, the problem, are functions of time. Okay, they change with time. And so these functions, these variables are related to each other through some kind of equation. Okay, could be some, and you'll see some similar equations today that you've seen before in other classes. And now, do we think about these, how these functions change with time? So if these variables themselves are related to each other, these equations, then their rates of change with respect to time are also related to each other. And so this equation, so what we'll do is usually take that equation relates all the variables, take the derivative of it with respect to time, and get what's called a related rate equation, which gives how the rates are related to each other as well. So to solve a problem like this, and this is also kind of a good strategy for solving problems in general, is first thing you want to do is read through a problem, is kind of organize information in a graph or a table, whichever is appropriate. And there are a couple reasons for this. One thing, it helps you kind of put things in your own words, set up in your own mind, the way your thing should be hopefully set up correctly. So you make sure you understand what the information being given, and also to make sure you're not missing anything. Make sure you have everything you need. Then after we do that, determine and label your variables, and often be more than one. Okay. And also which one, and also determine from these variables which one is the one that's unknown, which one you don't know. And in these kind of problems doing here in this video, just gonna be one unknown, but in general, it could be more than one unknown. But here, there'll just be one. Determine which variable it is. Then after that, then determine the equation relates all your variables together. Once we have that equation, and take the derivative of that equation we just found, or just determined with respect to time, to obtain then what's called a related rate equation. Then once we do that, then that's gonna be our equation. We'll plug in what we know, and there'll be one unknown in that equation, plug everything else and find that unknown, and that will be our answer. And also, finally, always make sure you check your answer to make sure it's reasonable, make sure it's not, has a correct sign, if it's whether it should be positive or negative. Make sure the answer is reasonable, it's not too large or too small, and also make sure your units are correct, since most of these problems involve units, or many of them do. Okay, so now, first, before we actually solve our first one of these general equations, let's go over here to the right and kind of talk a bit about related rates in general. Okay, let's look at this example. Here, we're not going to go through the whole process. We're just thinking about related rates. Let's say this example, we have a circle is expanding or getting larger at a certain rate. Right, some specific rate. Okay, so the idea here, we have a circle. Okay, and so it's expanding at a certain rate with respect to time. So in say when time is called t time, time equals 0. It's right here. Then time equals, maybe t equals, that could be seconds, minutes, whatever. Okay, right here. Let's say this time right here, maybe this is time equals 1. All right. Of course, you also have a radius here. It's also, so if your circle is getting larger, it means your radius is getting larger. Okay, your radius is growing. All right. So that's the idea. So in this for example, so you have a circle that's getting larger all the time, it's expanding out. And things like this can happen sometimes in real life. Maybe if you drop like a drop of oil on water or something like that, or something, or maybe a shadow might be expanding like that. A circular shadow could be expanding like that as well. Okay. Now, going by related rate, so think about what's the area of a circle. Of course, most of you are familiar with the area of the circle. The area of a circle, A, is equal to pi r squared. Okay, that's our area. Now here, once again, both the area, since it's expanding, both our radius or diameter, whichever one you use, we use the radius here, is increasing with time. And then also, that means also our area is also increasing with time. Okay, so our area is a function of time. Okay, then our radius is also a function of time. Let's call those A of t and R of t. Okay. So this is the equation, of course, that relates the area to the radius. Now, what we're going to do then is let's take the derivative, let's say with respect to time, okay, of this. So the derivative with respect to time of both sides of A, and then the derivative with respect to time of the other side, pi r squared. Of course, remember pi is a constant. Okay. Now the derivative of A, of course, think of the chain rule. Once again, of course, the derivative of A itself is just 1. Then, of course, that's going to be the derivative of A with respect to time, or how A changes, the area changes with respect to time. We do this, of course, pi is a constant. And then, of course, the derivative of r squared is, of course, first 2 times r. And then derivative, since r is a function of time, derivative of r with respect to time is dr dt from the chain rule. Okay. And so let's just pull the 2 out front and make it look a bit better. So we have 2 pi r dr dt. And this is our related rate equation. Okay, so this is the equation then that tells us how the area changes with the time, how the area changing with time is related to how the radius changing with time. Okay, so now then, if we want to solve a problem like this, since we have the variables we have, of course, we have 3 things. Eventually, could be variables. So this rate here, the derivative of the rate of how A changes, the area changes with time, or the rate of how the radius changes with time, or just r itself at some point. So we need to know at least 2 of those to find the third one. Okay, so the question might be something like, how quickly does the area change with time? At when the radius is a certain value, and we also know the rate that the radius changes with time, or maybe we know the area how quickly the area changes with time, and at that same radius, we know how fast the radius is changing with time. That will also give us that information. Okay, so that's the idea of related rate equation. So it's some equation that relates the rates with respect to time to each other. Okay, so let's take a look at our first example. Here we go. Okay, right. So this is our first kind of regular example problem like we're talking about here when we solve the strategy we have. All right, so this says, these problems I'm using were taken out of a textbook. It says a jet ascends at a 10-degree angle from the horizontal with an airspeed of 550 miles per hour. It basically means its speed along its direction is 550 miles an hour, not along the ground, but along the direction it's going. Okay. It says how fast is the altitude of the jet increasing? And then part 2, if the sun is directly overhead, how fast is the shadow of the jet moving on the ground? So once again, first, this is kind of a problem. We're talking about something in motion. So let's draw a picture to help us out. Okay. So we have a jet flying in this, let's say just flying in this direction right here. Okay. And if this is the ground, okay, it says moving at a 10-degree angle with respect to the ground. Okay. And this rate right here is it's going 550 miles per hour in this direction. Okay. Now the question about its altitude, let's think about this. It's actually going to make, of course, a right triangle here, as you imagine. Okay. So this altitude, let's call this y. This is the altitude, or its height above the ground. Okay. And also ask about the shadow. So let's say as the sun is right above. Okay. And this length right here is also the length of the shadow. Let's call it x for simplicity, but this is the length of the shadow. Now, one more thing before we move on. Since our speed is given in miles per hour, then remember these are lengths. Now, and also we point a direction, so it's going 500 miles an hour this way. And also let's call this r, this distance along here. Okay, that's what this represents. Okay, now, so since our speed is given in miles per hour, let's make our distances in miles. We don't have to, but that's going to make more sense than anything else. Our distances are in miles. Okay, so that's our first step. So draw a picture. Okay. All right, so we label our variables. So this distance right here is, and also I can call this r prime, like r prime of t. Okay, this distance is, the speed is this, and this distance is given by r. Altitude, the height above the ground, is given by y, and this is given by x. Now, which one of those are we trying to find? Well, actually, we have kind of two parts. So actually, first, let's make these a bit out of order. Let's actually find our equation that relates these two. Actually, no, I'll take it back, because basically you're going to use a slightly different equation for each one. So part A, want to find the altitude. Okay, so I want to find y. Okay, now, so let's just draw that triangle again, just a second. So once again, this is 10 degrees. This is r, y, and x. So I want to find the altitude, which of course we said is y. Okay, now, so here's where we find our equation relates all these together. All right, so now looking at this, what equation relates all these together? Well, think about what we know. We're looking for this one. Okay, then also we have the angle right here given by 10 degrees. And so what relates those, so we've got these two sides of a right triangle. And this is the opposite of that angle, this hypotenuse, so that's sine. Okay, so this tells us then that the sine of 10 degrees, remember the sine of 10 degrees is just a constant, since this there the angle is not a variable, equals y over r. Okay, now let's also do one more thing. Let's multiply both sides by r, and let's actually get this. So y, turn it around, y is equal to the sine of 10 degrees times r. Okay, now in this case, x, we don't really need to know x. We don't know it anyway, but it's irrelevant for this. We're just trying to find this altitude, y. Okay, now once again, we're going to assume that both y and r are functions of time. They both change with time. Okay, now, so now let's take the derivative. I was writing WRT, that's for with respect to, so I don't do as much writing, with respect to time. Okay, so the derivative of y with respect to time is equal to, and the derivative of the right side with respect to time. And let's remember that sine of 10 degrees, that's just a constant. So we're not taking the derivative of sines. In this case, it's not a variable, not the sine of x or something like that, just sine of 10 degrees. Okay, of course, the derivative of y then is dy dt. Okay. Let's see. Oh, actually, I realized I said something wrong. So the question was, didn't want to find altitude. It actually wanted to um, find the rate that the altitude increases. And that would actually be, then, that actually be y prime or dy over dt. Okay. Like, let me write it that way. So that would actually be dy over dt. Okay, so that's actually what we're looking for. Okay, so, and that's equal to, so we're sine of 10 degrees is a constant, so the sine of 10 degrees times dr, and derivative of r is dr over dt. So this is our related rate equation that relates it together. Okay, so now, do we have everything we need? Okay, well, we said that r prime, our dr, r is our hypotenuse, and the rate at which it's changing, okay, we call it r prime here, is 550 miles an hour. So we have that. Okay, we have that, and that's really the only thing our unknown is our dy over dt. So actually we have everything we need. So r prime, which is dr over dt, is equal to 550. I'm going to write this as miles over hours. Okay. And so plug that in, and that's going to be, it's also the sine of 10 degrees. Let's go to Desmos to help us with that. Or use your calculator. Make sure you're in degree mode. We'll talk about that as well. So in Desmos usually defaults to radian mode. So the way to change that is go up here in this little wrench in the upper right-hand corner. Click on that. You notice it says radians degrees. So let's change that to degrees. And then we just do the sine of 10. And we'll just use 2 decimal places, about 0.17. Okay, so the sine of 10 is about 0.17. This is going to be about 0.17. Of course, actually, sine doesn't have the units, unitless. And so times 550 miles over hours. And so 0.17 times 550 is approximately 93.5. The squiggly lines here, so 93.5. Once again, these are miles per hour. So we have the same units as we did. That makes sense. Okay. We said to double check our answer, make sure it's reasonable and makes sense. How do we know if it's reasonable? Well, one thing, it definitely should be smaller than our speed along the direction. That, of course, makes sense. And it's a fairly small angle, 10 degrees, so it's not going to be very large compared to our overall speed, and that's also true. It also should be positive, and it is, so forth. And also our units are correct. So both speeds are in miles per hour. Okay. Now, let's actually do part B. And actually, I need to move this down. Look here. Okay. Let's do part B. And part B is very similar. We probably won't take as much time explaining it. Sorry, I don't know what's going on with that. Part B. Okay, so part B, let's go back to our picture, original picture. This one said we wanted to do is basically the idea of they have the sun directly overhead. So we have a shadow right here below the airplane. And the idea that the shadow is also moving at a certain speed. Okay, how fast the shadow of the jet moving on the ground. Okay, so that one is asking about not actually the length, but how fast is, let's say, how fast is the shadow? And once again, so what we're looking for here, since the length of the shadow is x, we're looking for dx over dt. That's what we're trying to find. Also, one more reason why I said it's important that we wrote this is we're finding the rate. Like previously, the altitude increases, not the altitude itself, because to find the altitude itself, we'd actually have to know at a certain time. So there's no the rate, and we know at a certain time to actually find the true length. Okay. Now, let's draw a picture like we did before. Okay, a right triangle. So this is 10 degrees. Here's r. This time we have x. Okay. And once again, what relates r, the angle, and x? Of course, that's cosine. So cosine of 10 degrees is going to be equal to x over r, the adjacent side over the hypotenuse. Multiply both sides by r. We have x is equal to the cosine of 10 degrees times r. And this works just like the last one. Okay. Once again, I'll say just to take the derivative with respect to time. Okay, I actually need to move this down a bit more. So let me just do that. Down to the next page. No, it's there. Good. Okay. So like I said, this part works just like the previous part A. Okay. And so this time I can actually show it. So the derivative of x is just going to be dx over dt. Once again, cosine 10, like sine of 10 before, is a constant. So that's be cosine of 10 degrees. And then the derivative of r is going to be, of course, dr dt. So once again, this works just like the previous one. And so this is going to be the same speed, dr over dt. So the cosine of 10 degrees times 550 miles per hour. And also this case, we'll just plug it in our calculator like this. Actually, right now, this is exact, but it won't be an approximation once we do this. This is still exact, but our answer is going to be an approximate. Let's go to Desmos. Okay, so we can just type in, we're still in degree mode, so cosine of 10 degrees. Actually, put the 500 here first so to make sure it's clear to make sure I'm not putting 10 cosine of 10, 20, 10 times 500, so 550 times that. Okay, good. So that's 541. Let's go to do places 0.64, 541.64. This is 541.64. Our units are the same, nothing changed, so miles per hour. And once again, is that reasonable? Let's go, it's positive, it should be. And looking back at original picture, of course, this, the R as our hypotenuse should always be the longest side, so it's less than that. And this is a small angle, so it's not that much less than R. So that all makes sense. Okay. So that was our first example. So also showed how our basic procedure works. Now, let's take a look at this one. All right, this one says we're draining a tank. So we have a tank shaped in the shape of a cone. It says an inverted conical water tank with a height of 12 feet and radius of 6 feet is drained through a hole in the vertex. Right down here, the vertex is at the bottom, at a rate of 2 feet cubed per second. So this is important here, units here, because remember, volume is given in units of length cubed, so feet cubed, and it's a rate per time, in this case per second. So for the previous example, we had per hour, this is actually per second, and that's going to be a constant rate. What is the rate of change of the water depth when the water depth is 3 feet? Okay, so the idea is maybe the water is starting out up here at the very top and it's draining, and it's draining this constant rate. Then when the water is 3 feet deep, then how fast? So basically, a couple things are different. So this is the rate right here, outflow, the rate which it drains out the bottom, but the rate that the height is changing is not the same as 2 feet. That's going to be different. Okay, so the question is, what is the rate of change of the water depth? What's the change in height as at a certain specific when the water depth is 3 feet? So let's actually draw a picture. Let's do that over here of what we're talking about. So over here, I'll just say later. We don't know exactly when later. Then here's our, no, change that. So here is our cone, and basically here is our water. Make it kind of rippling look like water. Okay. Now at this point, our depth is going to be 3 feet. It says our height or the depth of the water is going to be 3 feet. Okay. Now we also have some radius right here. Okay, which I actually will be able to figure out here in a moment. Okay. Now we can also make a triangle, as you see here it does, the sides, make a right triangle. Okay, and once again the outflow, and this is once again 2 cubed per second. And of course, you want to find, this is the height, let's call this h. Okay, h equals 3 feet. Find dh dt, how fast the water is changing, height is changing per second. Also think about what the unit should be. Okay, so our volume is in cubic feet, our height is in feet, so it's changing per unit time. And here it's given our overall rate is coming out, it's given in terms of second. So this is going to be basically in feet per second. Let's make sure we get that at the end. Okay, now it actually gives a hint. It says use similar triangles. What that means then, well, first of all, let me show you the thing. So next, let's actually find our equation that relates all these together. And the volume of a circular cone like this, the formula for that, you may have seen this before, is going to be actually pi over 3 times the radius squared times height. Okay. And also radius is also in feet. Okay, that's our volume. Now, The problem, as we'll see here in just a moment, is actually with our related rate is actually right now, we don't really know everything we need to solve it just simply this way. I'll explain what I mean. So now let's actually take the derivative. And this will be able to practice in taking the derivative. Once again, with respect to time, WRT time. Okay. So the derivative of both sides with respect to time. Okay. Now, one reason I'm showing you this is because we'll see we'd actually end up having too many unknowns. All right. Of course, this side, of course, is just going to be the derivative of the volume with respect to time. Okay. Now, of course, here pi over 3 is a constant, so pull that out. But what we're going to have to do then is both the radius and the height are functions of time. And also, I should mention over here that, of course, all three, volume is a function of time, radius is a function of time, and then the height is a function of time. Okay. Now, so what that means, we take the derivative, actually, you have to use the product rule. Okay. So the derivative of r squared is 2 times r. Then the derivative with the chain rule, derivative of r with respect to time, is dr over dt. Okay. Then plus, and then, oh, I'm sorry, still have an h there. Don't forget that part. Then times h. So the derivative of the first function times the second. Then plus the first function, which can just be r squared times the derivative of the first, which is derivative of h with respect to time is just dh over dt. Okay. Now, why am I showing you this? Well, because right here, problem is, actually, let's erase this. We actually have too many unknowns. Okay. A few things we do know. So now that we see this, well, actually, let me write. Sorry, I should have written it. No, I was going to what to do. I was going to do. So this is going to look like this. Okay. So pi over q3, and just let's rewrite it. So 2r dr over dt times h plus r squared times dh over dt. Now, why am I saying that? Well, look back what our problem gives us. Okay. It tells us it wants us to find the rate that the height is changing. Okay. As specifically when the height is 3 feet. Okay. Now, also doesn't tell us what the radius is at that point. That's important. Okay. It also doesn't tell us how the radius is changing. Look what we have here then. Okay. We know the height is 3 feet we're interested in. We also know this dv over dt, that's actually going to be our rate right here. It's leaving the cone, dv over dt. Okay. So what is that? That's that rate is flowing out of the cone. But we don't know what r is. We don't know what, and we're actually looking for dh over t. That's what we're trying to find. The things we don't know what r is. We don't know what dr dt is. So that's a problem. So here, this way, we have too many unknowns. That happens sometimes. It's not so much that we have too many variables. We just have too many of the variables we don't know what they are. We're not given that. So too many unknowns. Okay, so how do we fix that problem? Well, we do this another way. So once again, it says we're going to use similar triangles to write the radius r in terms of h. Okay, let's explain that. So first off, look back at our picture. What's going to happen with this cone? Okay, if you notice, they're showing right here in our picture. We have with a triangle. Okay, and so this triangle will start as basically the entire cone is going to be the radius is 6 feet, the height is 12 feet, and of course, then we have some angle right here. We have this triangle. Now, what's going to happen is the water level decreases. That angle is always going to be the same. Okay, so we're always going to get a similar triangle, no matter how tall the water is. Always have a similar triangle. Okay, so we're going to see then, if you notice that the radius is half of the height. That's always going to be true no matter what the water level is. The radius is always going to be half of the height. Okay. What we can say then is that so R is always 1/2 h. So R is equal to 1/2 h. Okay, so what that does, it actually reduces our variables by 1. So we can write R as a function of h. And once again, I need to move this stuff down. So give me a second here again. There we go. Plenty of room. Okay. So what I'm going to do then, what that's allowed me to do, is say, so I can write, or say plug this into the volume formula. Okay. And so we have, remember our volume was pi over 3 times r squared times h. Okay. So you need to figure out r squared. So then if r is equal to h over 2, then if we square both those, r is going to be h over 2 squared, which is going to be h squared over 4. Okay. So plug that in. And then that's going to be where the volume is equal to pi over 3, and then times h squared over 4 times h. And multiply that together. So multiply fractions across. 3 times 4 is 12. And so we're going to have pi over 12. And then h squared times h the first is going to be h cubed. Okay. So now this is much easier to work with. So now let's take the derivative. As we'll see now, we'll have everything we need. Okay. So I'm not going to write the next shorten this out a bit. So the derivative of d with respect to time is just going to be dv over dt. Okay. Then, of course, pi over 12 is a constant, so pi over 12. Then the derivative of h cubed is going to be first 3 times h squared. And then the chain rule, derivative of h with respect to time is going to be dh over dt. So let's clean this up a bit, combine some things. And so this is going to be 3 over 12, which is going to be 1/4. This is going to be pi over 4 times h squared times dh over dt. Okay. And now this is our related rate equation. Relates how quickly the volume changes to how quickly the height changes. And once again, we're asking a specific height. We have that. So you notice we no longer have the radius or the rate of change of the radius here in this equation, unlike we did in the previous equation. So that's why this one will work. Okay. Now, actually, almost there. And actually, one other thing we should have mentioned, so I should have go back and change something. This is, and depending on how you want to approach this, but not a huge deal. But actually, let's make this dv over dt negative, because it's negative specifically because we're losing volume, right? So the rate of change of volume is actually negative. It's losing, instead of increasing, it's decreasing. Let's actually make that negative. Okay. Now, remember what it was we're trying to find. We know the rate of change of the volume with respect to time. It's this -2 feet cubed per second. We're trying to find the rate of change of the height. Okay. Specifically, when the height is 3 feet, how fast is the height falling? How fast is it changing? Okay. So it also makes sense the height is going less. Our final result should also be negative. Okay. So we do just have to plug in what we have. Okay. So dv dt is going to be -2 feet per second, feet cubed per second, is equal to pi over 4 times h squared. And I guess I probably should have just, let's do this a bit different. Doesn't matter, but so before I plug things in, let's just solve this for algebra practice. So let's solve this, get the dh dt by itself. Okay. And so if I multiply both sides by pi over 4, I'm going to have, so dh over dt is going to be, if I multiply both sides by pi over 4, or divide both sides by pi over 4, that's going to be 4 over pi. And then times over h squared. You can check this on your own. Okay. Then times dv over dt. Okay. Now let's plug everything in. Let's put everything on the same side. So 4 over pi. And here, we, of course, have 3 feet squared, the height at the moment we care about. And this would be negative 2 feet cubed per second. Okay, we'll check with Desmos here in a minute to multiply all this out. Okay. Let's do a bit more right here. So, of course, it's still going to be 4 over pi. And, of course, 3 squared is going to be 9 square feet. And then here, this is negative 2 feet cubed over seconds. So what's going to happen? 2 of our square feet are going to cancel out. This just become 1 foot. Okay. And feet cubed or feet squared just leaves 1 foot on top. We have seconds on the bottom. I'll make sure we have the right units. Let's go to Desmos and make sure this works. And so let's actually, I guess we can clean up a bit more before we do that. So here we're going to have 4 times negative 2 is going to be negative 8 up here. And then down here, we're going to have 9 times pi. And this is going to be, we'll lift our units are feet per second. That's what we said it should be in. Okay. Now that's equal. That's exact, but let's approximate that. Negative 8 over 9 pi. So negative 8 divided by 9, and then do a pi, just type in the letters pi. And that's going to be about negative, let's use 2 places again for simplicity, about negative 0.28. Okay, about negative 0.28, and that's going to be feet per second. That is the rate of change of the height with respect to time. So let's go back and take a look. Does that make sense? Well, it's negative. It should be. The height is decreasing, and that seems reasonable. Okay, it's not a very big change per second. Once again, what this is asking is, at this moment, when the height is 3 feet, how quickly is the water level falling? About 2.28 feet per second at that moment. Okay, with this constant rate coming out the bottom. Okay. So get our next one. So one thing, this is a bit of a longer video, so just make sure you have to break it up if you need to take a look at part of it now, then part of it later. Okay. Well, this particular problem is not that long. All right. So this question asks, it says a drinking soda. What rate in inches cubed per second is a soda being sucked out of a cylindrical glass that is 6 inches tall and has a radius of 2 inches? Okay. So the glass, the depth of the soda decreases at a constant rate of 0.25 inches per second. So this time doesn't give us a picture. We'll just have to draw our own. So here's our glass. It's a cylindrical glass. Okay. Now it says the height of the glass is 6 feet. So 6 feet tall. Okay. Now let's also put right in here like a water level. Okay. So this is the level right here. Okay. Now this level right here, that's what we're going to call our H, our height. Okay. Or actually, the problem calls in the depth of the soda level. So that's fine. This is the depth. Okay. Let's call that D. And let's take a look at our units. What's our units be? Well, it says the radius, also the radius is 2 inches. So R equals 2 inches. So that makes sense. Our depth should be, and also our soda is decreasing at 0.25 inches per second, so our depth should be in inches. Okay, we're going to call it D in inches. Okay, and sorry, I put 6 feet over here. It should have been inches, definitely not 6 feet, 6 inches tall. And also it says it's 6 inches tall. Okay. Now, Same with what we know. What is we know? So we know we're also given the rate of change that soda decreases is 0.25 inches per second. So if we're calling D our depth here, okay, then D, the change of depth with respect to time should be that, I actually need to call it H because that would be D. So let's just call it H. Because we only have DD. So DH dt is going to be, like the previous example, this isn't something entirely necessary, but since the water level is falling, let's say that's going to be negative. So negative 0.25 inches per second. Okay, that's what we know. What we want to find then is we want to find the rate the soda is being sucked out. Okay, so basically that's the loss. The rate's being sucked out essentially is the loss in volume. This is a bit similar to the problem we just did, but kind of opposite. That probably knew the rate the volume was changing. We want to find the rate which the level is changing. In this case, it's the other way around. We know the rate at which the height is changing. We want to find the rate at which the volume is changing. So once again, we have a straw. Let's put it like this. We have a straw. And basically it's going out. So this is our dV dt is going out, okay, of our straw. So we want to find the change in volume with respect to time, okay? Now also, let's think about our units. What units should those be? Well, our volume is always length cubed, okay? So volume is going to be, if we're given length as inches, volume is going to be inches cubed, and since it's going to be a rate per unit time, what time we're using so far. In this case, our rate here is given in seconds. We use the same rate, so this can be inches cubed per second. So we want to make sure at the end of our problem we get the same units. Okay. Now, so we did determine, label our variables. The unknown variables we're trying to find, that's an unknown variable. Okay. Now, our equation. So of course the volume of a cylinder, all that V, is actually going to be pi r squared times h, okay, times the height. All right, and that's the formula. Now in this case, we know that r, our radius, is always going to be the same, okay? So radius is going to be 2 inches, okay? And so what that means then is that our volume is going to be, of course, radius 2 squared is going to be 4. So this is going to be 4 pi times h, okay? I'm just going to make sure you follow that. So the radius is known as 2 inches. And so radius squared is 2 times 2 is 4. Then our constant up front is going to be 4 pi times h, okay? Now, let's take the derivative. And so if we do that, our derivative is going to be dV dt, take the derivative of volume with respect to time. And the 4 pi is a constant, so we have 4 pi out front. The derivative of h is just going to be dH dt. This is a fairly simple one because we don't have a very complicated equation to work with. So this is our related rate equation. It relates the rate which the volume changes compared to relate the rate at which the height changes. Okay. In this case, the only thing I have to plug in is just this. So let's just plug in that. The rate at which the height changes, which is 0.25 inches per second. Okay. 4 pi. And I think, let's see, 4 pi. I think it was 0.25 inches per second. Now, we know our volume should be in inches cubed per second. You may be wondering where the other inches went. So actually what happens is when I multiply this here together, okay, this 4, so the radius is 2 inches, so radius squared, of course, is going to be, to square that, be 4 inches squared. So it's not really showed here right here, but this 4 is actually a 4 inches squared. So maybe I should actually write that in just to make sure it's clear. Let's put a little space. Okay, this 4 is actually 4 inches squared times pi. Okay, now let's make sure our units add up. And so that's going to be Inches squared times inches is inches cubed. Good. So those are units we need per second. And then 4 times negative 0.25 is going to be negative. And 4 times 0.5, you can check your calculator if you want, but that's just 1/4 of 4. That's just going to be 1. Okay. So the rate at which the volume changes, or the amount of volume being sucked out of the straw, okay, is going to be 1 inch cubed per second based on this rate. Okay. Once again, is that reasonable? It's negative. That makes sense. Okay. And that the rest of it kind of makes sense there. We have the correct units. So that looks good. Looks reasonable. Okay. One more problem, one final problem. So this one is going to be somewhat similar to the very first one we did, and this involve a triangle. All right. So this is about in baseball. So what it says, it gives us a picture below. So runners stand at first and second base in a baseball game. You know, if the ball is hit, the runner at the first base, this is first base right here, runs towards second base. He's trying to steal a base at 18 feet per second. That's his speed. And at the same time, the runner at second base is trying to go toward third base, trying to steal third base, and he's moving at a speed of 20 feet per second. Okay. Now it says how fast the distance between the runners changing 1 second after the ball is hit. Okay. It also tells us that basically they're 90 feet. Distance between the bases is 90 feet, and basically this makes a square. So what we're going to do is actually let's draw a picture. And let's actually, we're going to draw a 90-degree angle. Okay. So this is second base right here. This is third, and this is first. So we're just kind of changing our picture around. Okay. Now, what's happening is kind of relabel our picture. Okay. Is we have runner number 1. Let's call this runner number 1. Okay. And his speed, and since let's call that y, dy dt, let's call his speed dy dt, is going to be, he says he's going at 18 feet per second. Okay. So he's running 18 feet per second, starting at first base, running in this direction. Okay. Now, we'll plug in the numbers here in just a minute, but let's think about it this way. So, and if I'm going from second to third, let's say this runner is number 2. Okay, call this runner number 2, headed this direction toward third. Okay. And let's just call that, for simplicity, let's call that direction x. Let's call that dx of dt is equal to something. Now, also for simplicity, let's think of it this way. So let's make this kind of conventional with our usual sense of direction. So let's say this is the positive x direction. So the second runner is running at 20 feet per second, a positive 20 feet per second. Okay. So let's say this is negative. This runner is running at a negative 18 feet per second since base is going downward. Okay. Once again, that's just a choice. Now the question is about the distance between them. Okay. So this length right here is, let's call this r. Okay. We should also call it d. Let's call it r. Right. Of course, this length here is x, and this length is y, this distance. Okay. Now, so what's happening, let's kind of draw another picture over here really quickly. So what's happening is as these runners run, so at one point, you know, so maybe at, like, say, we'll say at some point, let's say maybe t equals 1 second, maybe it looks like this. Okay, this is when it looks like that. Let's actually change colors. So maybe at 2 seconds, say t equals 2 seconds, maybe it looks like this. Maybe this screen looks like that. Basically, keep making a triangle. Maybe at 3 seconds, let's do one more. Okay, so basically this runner number 1, runner number 2 is getting closer to third. Runner number 1 is getting closer to second. So maybe at t equals 3 seconds, looks something like this. Okay, get the idea that this is between them. What they're always doing, though, is always creating a triangle here with respect to the what we're calling x and y axes. Okay. Now, so let's say what it is we're trying to find. So let's go back to our information. This kind of gives us a picture of what is going on. to black as well. So go back up here. Okay. Now it says how fast the distance between runners changing at 1 second after the ball is hit. Okay. Okay, so this distance is r. What we're trying to find is I want to find, okay, at t equals 1 second, I want to find dr dt, how fast the distance is changing between them. Okay. Now, a couple more things we need to know. So first, actually, in this case, it may be more sense to actually let's go ahead and actually write out our rate, our equation, actually find a related rate equation, then we'll fill in some other details. Let's take a look. All right. So I think most of us know that from triangles, what this is relates, what relates the sides of a right triangle is basic Pythagorean theorem. Okay. Okay. From the Pythagorean theorem, okay, that's going to be r squared. This is between them is going to be x squared plus y squared. Okay. Now, if you take the square root of both sides, r is going to be plus the square root of x squared plus y squared is going to be plus, because of course r is going to be a distance that has to be positive. In general, take the square root of both sides to be plus or minus, but in this case, it's got to be positive. Okay, so r is going to be greater than 0. Let's make a note of that. Okay, so now let's take the derivative with respect to time. Okay, so now let's kind of do this in steps. And also one more thing, I'm also going to write this, or the square root, be writing as a 1/2 power. So I'm going to do that. So this is going to be x squared plus y squared to the 1/2 power. Okay. Now, on the left side, that's just going to be dr dt, which of course is what we're trying to find. Okay. Now here, take the square root of something, the 1/2 power is going to be 1/2 times a something, which is x squared plus y squared. Okay. Times, or to the power, so 1/2 minus 1 is negative 1/2. Then the chain rule, the derivative of what's inside. Okay. So the derivative of x squared is going to be 2x. And then with the chain rule also, x is changing with respect to time. That's going to be times dx over dt. Plus, and this is going to be basically identical just with a y. Derivative of y squared is 2y. And once again, since y is changing with respect to time, times using the chain rule dy over dt. Okay. And we just kind of make it look a little bit nicer. So I have a big fraction. So we're going to have 2x times dx over dt, okay, plus 2y over dy over dt. Okay, then down here, we're going to have 2. Now I put this in terms of a square root, x squared plus y squared. Okay. Now, let's take a look at what we have. So remember, the dr dt is what we're trying to find. So we just need to figure out everything on this side. Now, we know the dx dt and dy over t, those are our speeds given. Okay. So dy dt is right here, dx dt is that. But we also need to know x and y. You notice that. Okay, but also asks for x and y. Okay. So specifically, we need x and y at t equals 1 second. Also, one more thing I should have said, we need, want to find dr dt, and that dr dt, since it's a speed, should be the same units as our other speeds in feet per second. I should have said that before. We have to make sure that's true at the end. Okay, so how do we find x and y at 1 second? We're going to use, if you remember, distance equals rate times time. where d equals RT. You've learned that before. The distance equals, just remember, rate times time. Okay. Or just a lot of times just called d equals RT. Okay. So remember those x and y are distances. So x is going to be dx over dt at 1 second. Okay. And that's just going to be dx over dt. Let's go back and see what that was. That was the 20 feet per second. Yeah, 20 feet per second. 20 feet per second. Also, it's a distance that should be in just feet. Make sure that's going to be true. Times 1 second. Our seconds cancel out. Right, so just 20 feet. Okay. Now, y is just a bit different, and we'll explain why. Let's go back and take a look. Now, it's still going to be distance rate times time, but it's going to be a little bit different. Okay. Now, if you notice, we're starting out, the way our triangle works right here, think of this spot as 0 right here. This is 0, 0. Okay, this is our essentially our origin right here of our triangle. Okay, this one then starts from 0. But this one, runner first, starts actually from 90. Remember, I said that we have 90 feet between each base. And so here, actually starting from 90. So basically what's going to happen, imagine here, this one, x, since it starts here at 0, is going from 0 to 90 feet if it makes it to third base. But y is actually going from 90 down to 0. So the way to do that just could be essentially 90 minus the distance he runs in that time. Okay, so y then is going to be just a bit different. It's still going to be dx over dt in a sense, but basically it's going to be 90 minus dy dt times 1 second. Okay, it's basically subtracting the distance the person runs, subtracting that from 90. Okay, starting out at 90 feet from second base, and then however distance he runs, you're taking that away from 90, if that's what we're showing. And basically, eventually after enough seconds, this is going to go to 0. All right. And so that's going to be 90. That's also going to be 90 feet minus 18 feet per second times 1 second. Once again, seconds cancel out. So 90 minus 18 is 72. You check that, but it's 72 feet. Okay, so now basically we're pretty much done. Okay, we have to plug everything in, but basically we have everything we need. Okay, well, this one has been definitely been a pain. It takes a little while to do, but we're almost there. So let's plug everything in. And we're also going to go to Desmos to help us out with that. Let's plug everything in here. Okay, so up here we have 2x times dx dt. So 2 times x, which is, we said x is 20 feet, times dx dt, which is 18 feet per second. Plus 2 times y, which is 72 feet, times, remember, this is negative, and negative, wait, no, I got the backwards. Sorry, x is 20 feet per second, and there we go. This is 20, this is negative 18 feet per second. Okay, then down here, we have to go on our square root, and that's everything squared, so x squared, which is 20 feet squared, plus 72 feet squared, and the square root of that. Okay, so like I said, let's go to Desmos. I'm going to show you how to plug all that in on Desmos to make it a little bit easier to work with. Okay, so go right here. All right, let's put parentheses. So we had 2 times 20 times feet times also 20 over the rate. Okay, and that was minus. Let's double check that. Yeah, 2 times 20 times 20 plus 2 times 72 times negative 18. So let's put that as a minus times 2 times 72 times 18. Hang on a second. I didn't mean to do that. There we go. That's the wrong thing. Minus 2 times 72 times 18. Okay. And now we're going to divide that by, and what it's going to do is square root. You can either find the square root in the functions or just type SQRT, but if you go to the function, it's actually just right here. Close that. And so that's going to be 20 squared plus 72 squared. Okay. And that should be our answer. Now, notice is negative. What that means then is actually the distance between them is actually at 1 second is actually decreasing. Okay. So plug all that in. Negative 23.98 was approximately 3.98. Now, let's make sure our units are correct. Now, if you notice up here on top, what we have are actually, on top, we combine everything, we actually have feet squared per second, which is not what we want. Down here on the bottom, of course, inside we have feet squared, and the square root of that is just feet. Okay, so 1 foot goes away, left of feet per second. That's what we need. So feet per second. So now, once again, at that moment, what it says is actually the distance between them is actually decreasing at that particular moment and 1 second after. That may be true 2 seconds, 3 seconds after as well. At that moment, though, the distance between them is actually decreasing. Okay. So I know this has been a long video. If you watch the whole thing, we're going to break it up in parts. But what we learned then is about related rate problems, what it means for we have variables that are related by some equation to each other. And then we take the derivative of that equation with respect to time. That gives us what's called the related rate equation, which tells us how those rates of things change, how they're related to each other. We learn basically a process to go through and solve related rate problems like that. Thank you. Have a good day.